In this section, I'd like to explain the heat equations. We consider temperature distributions in the y-years. In the y-years, heat is transferred by conduction from the high temperature region to a low temperature regions. So U is the temperatures, and at the both end of the y-years, temperature is fixed to become the zero. The length of the y-year is a capital L. To describe the time evolution of the temperatures, we use a heat equations. Heat equation is a linear second-order partial differential equations. U is a function of x and t. We consider the thin y-years, so we just only consider one-dimensional y-years. This is a heat equation. Other initial conditions, temperature distributions in the y-year is given by the fx, and the x is in the range of the 0 to the capital L. This is the length of our y-years. As a boundary conditions, at the both end of the y-years, temperature is a 0. This is the boundary conditions. So we have a differential equations, initial conditions, and the boundary conditions. To solve the differential equations, we use a separation of variable method. Substitute the product of the two functions. Capital X is a function of x. Capital T is a function of t. Substitute into the partial differential equations. So round U, round t becomes x t primes. And the k second derivative of u with respect to x becomes k x2 prime t. Then substitute into the differential equation, it becomes x t prime equal k x2 prime t. So from this equation, you have this equations. And the left hand side is a function of t alone. Right hand side is a function of the x alone. To satisfy this have to be equal to the constant values. As a constant value, we choose the minus lambdas. From the single equations, we derive the two equations for the capital X and the equation for the capital T. When the lambda equals 0, we can easily solve the equation for the capital X is a c sub 1 plus c sub 2x. When the lambda is a negative alpha squares, then capital X becomes c sub 1 hyperbolic cosine alpha x plus c sub 2 hyperbolic sine alpha x. When the lambda is a positive quantity, alpha squares, capital X becomes c sub 1 cosine alpha x plus c sub 2 sine alpha x. Then we can apply the boundary condition. At the boundary, you can substitute u0t becomes x0 t equals 0. So from these equations, capital X becomes 0 at the x equals 0. And then another boundary condition. At the x equals capital L, this becomes 0. So from these conditions, capital X becomes 0 at the x equals capital L. Then we apply the boundary condition to each solutions. When the lambda equals 0, capital X is c sub 1 plus c sub x, then capital X have to become 0. Also lambda is a negative quantity. Then again, capital X have to become 0. When the lambda is a positive quantities, then without having the capital X equals 0, we have a solutions. From this expression, by applying the boundary condition, c sub 1 have to be 0. But c sub 2 does not have to be 0. Instead, sine alpha L could be 0. So to satisfy these equations, alpha L is an integer multiple of the pi's. So from this equation, you can find the eigenvalues because lambda equal alpha squares. So as eigenvalues, we have n pi over capital L squares. So using the eigenvalues, we could write down the equation for the capital X is a c sub 2 sine n pi over L times x. As n, you can substitute 1, 2, 3, the integers. Then we could solve the equation for the capital T's. this is a really simple equations. First order differential equations is expressed capital T equals C sub 3 times exponential minus k. This is a lambda n pi over L squares times t's. Then you can substitute back into the expression for the u. U is expressed the product of the capital X and capital T is expressed this equation. As a constant coefficient, we choose the a sub n. And the general solution is given by the summing up all the value of the n. N could be 1, 2, 3 integer. So we can express the general solutions by summing of all the possible solutions. So by substituting this u into these equations as a general solution, we have this expression. Then we need to determine that this a sub n. A sub n could be determined by applying the initial condition. If you substitute t equals 0, so this is t equals 0 into the general solutions, it becomes sigma a sub n sine n pi over Lx equal fx. This is the initial condition. From this equation, you can multiply the sine m pi over Lx in the both sides of the equations and the integrals. And the integrals 0 to the L n equal 1 to the infinity a sub n sine n pi over Lx times sine m pi over Lx dx equal integrals fx sine m pi over Lx dx 0 to the L. And this part becomes L over 2 a sub m because the trigonometric function of the sine is orthogonal. So we have to take only the same value of the m. So it becomes, we choose only the m equal n. From this equation, a sub m becomes 2 over L integral fx sine m pi over Lx dx. So we discover the coefficient of the a sub m. Then you can substitute this a sub m into this equation to find the solution of the u as a function of x and t. So this is the solution. Once the initial condition is given, initial condition is correspond to the fx, then we could perform this integral to find out the temperature distribution in the y years. So this is a numerical result. As the initial conditions, initially we consider the constant temperature in the y years. The temperature is equal to the 100. And the heat is lost from both ends of y years. The temperature is decreasing with times. So this is times, and this is x. Initially, temperature is equal to the 100. And the temperature is decreasing because of both ends of the y year becomes t equals 0. And at t equals 1.4, this is the temperature distribution. At the centers, temperature becomes maximum. At the both ends of the y year, temperature becomes 0. To draw these figures, we use 100 terms. Actually, it is impossible to take into account of infinite number of terms. So general solutions is expressed to the infinite number of terms. Instead, we use 100 terms because the contribution of the other terms is not significant. So we only consider 100 terms to draw these figures. Okay, this is the end of this session.